Let's talk about Euler graphs. To understand Euler graph, you should understand Euler path. So what is an Euler path in a graph is like this. A path is called Euler path if it covers or visits every edge of the graph exactly once. That means your path should visit every edge of the graph exactly once. Okay, not more than that, not less than that. That means we have to visit every edge. Because we have to visit it exactly once means we should visit everything, but we should not repeat the edges. Okay, let's try to draw a path in this graph which covers every edge exactly once. I do that like this: A to B, let's say B to C, C to D, D to E, E to F, F to C, then C to A to F. I covered every edge exactly once, isn't it? Did I miss any edge? No. Did I visit any edge twice? No. Then definitely it is Euler path. We started at A and ended at F, right? So it's a path which is not circuit. What is circuit? Circuit is a path which starts and ends at the same place, right? And no repetition of edges. So that's why. So finally I got here Euler path. Note down that it is not a circuit. What about this graph? Let's try. Let me begin at any point because it's a symmetric structure. Every vertex has same degree. Then let's begin with A and try A to B, then B to C, then C to D, D to B. I got blocked, right? So maybe I did a mistake, and let's try in a different way. D to A, then A to C. Again I got blocked. So I know that this graph doesn't have Euler path or Euler circuit. Okay, so you take this graph and try to find out Euler path. It is impossible. Okay, so finally this graph doesn't have Euler path. So now how to find out whether some graph has Euler path or circuit, and how to know that some graph has Euler circuit? That's the question. Okay, so what kind of graphs will have that property? Okay, we'll see that. So before going to a very strong theorem which easily find out, using that easily find out whether a graph has Euler path or not, before that we'll try to develop some intuition behind that theorem. There is a relation between Euler path in the graph and degrees of vertices. We'll see that. Before that I'll take a graph and I will show you the Euler path. After that I will compute degrees with that Euler path. Then after that we'll observe the relation between that Euler path and degrees. Okay, so this is a graph. First I draw the Euler path: B to C, C to F, F to E, E to B, B to A to D, D to E. Let me do that. B, C, F, E, then go to B, then A, after that D, after that E. Okay, so the property of Euler path is this path covers every edge exactly once, right? Then using this path I can construct the degrees. Okay, so the advantage of doing that I will tell you. Before that, let me do the calculation first. I'll take 6 vertices: A, B, C, D, E, F. Okay, now start calculating degrees of every vertex by one by observing every edge. Let's start with this edge. It is between B to C, right? Then B gets 1 in its degree and C gets 1, isn't it? So this degree is this edge is processed. Then process this edge CF. Because of that C gets plus 1, right? F gets plus 1. Now process this edge, then because of that F gets again plus 1 and E now gets plus 1, right? Now let's process this one, then immediately E gets plus 1, B gets plus 1. After that B to A, because of that this edge, now B gets plus 1 and A gets plus 1. Now because of this edge, A gets plus 1 and D gets plus 1. Now because of this edge, D gets plus 1 and E gets plus 1, isn't it? Now see. Just focus on this intermediate vertices C, F, E, B, A, D. Okay. So when you calculated degree of this edge, immediately you calculated degree of this edge, right? I mean effective degree. Then C got +2, you see, because of two edges associated to it. Similarly, while calculating, degree of, degree contribution of this edge and this edge, F got +2, right? In that way, every intermediate vertex C, F, E, B, A, D got its degrees correctly, but in +2 form. But whereas B got its degree in this form. First, initially B got +1. After that, every time whenever you encounter B, you got +2, right? Now, similarly, E also. So here it got +2, but at the end it got +1, right? So that's why here +1 followed by +2. What I want to say is, other than ends, every intermediate vertex gets its degrees in +2 form, right? +2, +2, +2, so on. So that every intermediate vertex degree definitely will be even number. Now let's focus on the last and first vertices B comma E. B gets +1 first, after that some even numbers, then overall it will become odd number. Similarly, this end also gets 1 +1, after that even numbers, then it gets odd number. Okay. So in this process, finally you got two vertices with odd degree and all other vertices with even degrees. Okay. So I can now confirm this thing. What is that? Whenever you have an Euler path in such graph, every vertex other than two vertices, every vertex degree is supposed to be even. Yes. So let's take one more graph and we'll observe the same, and we'll try to understand this concept clearly. See this graph, and in this graph, hello. See this graph and we'll try to find out Euler path in this one. A to B, then B to C, C to D, D to E, E to F. After that I'll go to F to C, C to E, E to B, B to F, F to A, right? So I got Euler path. So that path is this one, okay? And starting vertex equal to ending vertex in this graph. Such Euler path, which is nothing but Euler circuit, isn't it? Now when you have that Euler circuit, what happens to this degree calculations, we'll see. So we know that because of this edge A gets 1, right? Then immediately after that, for all intermediate vertices, directly I can say that this vertex B gets now degree 2 here because of this edge, right? Then +2. Now point mark C, because of this C, C gets this, +1 because of this edge, +1 because of this edge. Let's write 2 in that way. Now D gets 2, then E gets 2, F gets this one 2, C gets 2, E gets this one, right, 2. Then B gets this one and this one 2, in that way. So F gets 2 and now A gets only 1. But already A got 1 because of starting vertex. Since it is again ending vertex, that +1 will become even number. So what I want to say is, all these vertices definitely gets even contribution. Generally end vertices won't get even contribution because end vertices gets +1s, so they get odd numbers, right? But whenever the starting vertex equal to ending vertex, when you form Euler circuit, then you get two such +1s, which makes again even number. Then every vertex degree automatically will become even number. So these are the two observations. One is, when you have Euler path which is not circuit, okay, in a graph, then there can be at most two ends which are different, and because of that you get at most two odd degree vertices. Second one, if you have Euler path which is circuit, then starting vertex equal to ending vertex, then it's also that vertex also gets even number. So every vertex gets even degree, correct? So finally this is about Euler paths and degrees. Let me write here. Whenever a graph has Euler path, okay, let's say graph has Euler path, then definitely there exist, there are at least two not at least, right, at maximum 2. There are at most 2 odd degree vertices, that you should remember. Okay, that is what we observed. And if that path becomes circuit, then definitely you get this kind of thing, and every vertex degree is even. Let's consolidate all these things. First, I define what is Euler graph now. Euler graph is a graph which has Euler path. That path may be circuit, may not be, we don't know, but definitely there is a path. That is about Euler graphs. Now, whenever a graph is Euler graph, then there is very important observation. We can connect that graphs with, odd degree vertices in it. So this is very important theorem. So using this theorem, always we can find out whether a graph is Euler graph or not. We'll see that theorem. A connected graph is Euler graph if and only if it has at most 2 odd degree vertices. Okay. So here if and only if has very much significance. It's a two-directional thing. That means if a connected graph is Euler graph, then definitely the number of odd degree vertices in the graph is at most 2. Reverse direction. So it's a two-directional thing. Okay. Second one, start here. If any graph has at most 2 odd degree vertices, definitely there is a graph will have Euler graph. Okay. So first direction is already done. We have seen the first direction, right? We have taken a graph with Euler path. So that graph is Euler graph. In that Euler graph, we have shown that there can be at most 2 odd degree vertices using the example. That is what we did. Now the reverse direction, whenever a graph has at most 2 odd degree vertices, then why such graph should have Euler path? So that part is a little bit complex thing, so I am not proving it, but you remember it as a result. So in GATE exam, so this remembering this result is sufficient. Just remember it. What is the theorem? In a connected graph, if it is Euler graph, if and only if it has at most 2 odd degree vertices. Example, how to apply this theorem we'll see. Let's take a random graph and apply find out the degrees, every vertex degree. This vertex degree 3, this one is 3, right? 1, 2, 3 and 1, 2, 3. This one 3, this one 2, this one 1, 2, 3, 4, 5, right? So this one is 2. So number of odd degree vertices are more than 2, right? Then see the if and only if thing. Graph is Euler graph if and only if you have at most 2 odd degree vertices, but you have more than that, then condition become false. If this is false, then graph is not Euler graph. That means there is no Euler path in it. We know that Euler graph is a graph which has Euler path. So you can't have Euler path. So let's take one more random example. 1, 2, 3, 4, 5, 6. Let's observe the degrees. Degree 2, degree 3, degree 2, degree 2, degree 3, degree 2. Yes. Number of odd degree vertices are at most 2. Then this condition become true. Then definitely this graph should be Euler graph. Then we have to, whenever a graph is Euler graph, there should be Euler path. We'll see whether there is Euler path or not. Let's begin at 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 1, 1 to 2, 2 to 3. Yes, there is a Euler path. We know that. So that is what the result. Okay, you remember this result so that any GATE question we can answer. But one more thing, graph should be connected. If graph is not connected, you can't have Euler path. So that graph cannot be Euler graph. Example, take this graph 1, 2, 3, 4, 5, 6, 7. Okay. So this graph is, now, if you see the number of, degree of every vertex, it will be even, right? Everywhere 2, 2, 2, 2, 2, 2, 2, all 2's. According to theorem, it has at most 2 odd degree vertices, correct? But that is not Euler graph. The reason, graph should be connected. So I can say that a connected graph is this if and only if is here. So we are talking about directly connected graphs. A connected graph is Euler graph if and only if this happens. Okay. Since this graph is not connected, so don't apply the theorem. Apply this theorem only to connected graphs. That is what I wanted to say. Okay. So this is the result about Euler graphs. Let's summarize the things about Euler graphs. You have a connected graph, let's say. Then that connected graph G if it in this graph, if the number of odd degree vertices are at most 2, okay, then definitely we know that that graph is Euler graph. But whenever the number of odd degree vertices are at most 2, then we can classify them into 3 parts, right? One is degree 0, that means number of odd degree vertices are 0, that means all are even, and number of odd degree vertices are 1. Third one exactly 2, okay, 2 odd degree vertices. So this case is impossible. The number of odd degree vertices cannot be 1. Why? In any graph, so when I taught sum of the degrees theorem, I taught this one. What is that? In a graph, the number of odd degree vertices are always even in the number. So that's why you can't have one odd degree vertex. Let's cancel it. Then only 2 cases. Whenever the graph is Euler graph, then we know that number of odd degree vertices are at most 2. Then all should be even, otherwise exactly 2 odd degree vertices. Okay, if every vertex degree is even, then definitely we can guarantee one more thing, that is Euler circuit. If there are 2 odd degree vertices, then easily we can map these to that ends, like maybe you have Euler path, right, and but not circuit. That's why starting vertex different from ending vertex. That's why while doing the degree calculation, 2 vertices gets odd degrees. Okay, so when there is a Euler circuit, then you will have Euler path, right? Then starting and ending same, then every vertex will get, because this end vertices also gets even degree, so every vertex degree will become even. That's the reason. So whenever you have 0 odd degree vertices, otherwise all vertices are even degrees, so Euler circuit is possible. And if you have exactly 2 odd degree vertices, then definitely there is a Euler path but not circuit. Here it is Euler path and circuit. So degree number of odd degree vertices 1 is impossible, we know that. And what about this case? Like, what if you have more than 2 odd degree vertices? In that case, that graph cannot be Euler graph. We are talking about Euler graphs, right? Only 2 cases arises. So if you remember this, then you can answer any gate question related to Euler graphs. We'll see one gate problem related to Euler graphs. Which of the following graph has an Euler circuit? And 4 options are given. We'll evaluate one by one. So really, a graph has Euler circuit. Then we know that just now we realized that the number of odd degree vertices in such graph should be definitely is 0, right? Number of odd degree vertices. That means every vertex degree should be even. That is necessary condition and sufficient, of course. So we'll see this option A, any k regular graph where k is even number. Example of regular graphs are like this, right? So this is a 2 regular graph. Okay. Now one more graph is cubic graph, like this. Let me connect this to here, this to here, and this to here, this to here. So here every vertex degree is 3, but it's a k regular graph, but k value 3, then this graph cannot have Euler circuit, correct? So the question is, that's why specially it is given that k is even number. So here k I took 2, right? It's a 2 regular graph. Yes. So it looks like option A is correct. But if you see this picture, you will understand that option A is wrong. What if the graph is disconnected? Because that is not mentioned in the option A. Let me take a graph which is disconnected, but every vertex degree even. So this is a k regular graph, but is it is this graph has Euler circuit? Impossible, because graph is not connected. Only connected graphs will have it, right? So that's why option A is wrong. But sometimes it won't strike to your mind, right? That's why go through all the options. Don't answer a question in a hurry mode. So if you have any doubt on option A, so just look into other options also. Let's see option B, a complete graph on 90 vertices. Any graph which is complete graph with n vertices, then every vertex degree will be n minus 1, right? Let's take a complete graph with 90 vertices. Then in complete graph every vertex degree is n minus 1. So since n value 90, it will become 89. So every vertex has 89 neighbors. Then number of odd degree vertices are, everything is odd degree vertex, and such vertices are 90. There are 90 odd degree vertices. Then how can you have Euler path or circuit? Impossible. So option B is eliminated. Go to option C. The complement of a cycle graph on 25 vertices. So we have to calculate complement of a cycle graph on 25 vertices. First focus on C25. Then we'll come to C25 bar. So C25 bar, whether this graph has Euler path or circuit, we'll see. Cycle can be drawn like this, right? So cycle has a symmetric structure. Okay, let's focus on a particular vertex X. What is the degree of this vertex X in C25? I know that I have to calculate degrees of C25 bar, but I will do that indirectly with this C25 calculation. So here every vertex is connected to two other vertices, then degrees 2, isn't it? There are 25 people in the group, so each vertex can be connected to at most 24, correct? Then if X is connected to two vertices here, then definitely in complement X is connected to other vertices, right? Other than YZ, how many vertices we have? Total 25. Remove X, 24. I am calculating degree of X. Then 24 minus 2 are gone because 2 are adjacent, two vertices are adjacent for X in C25. Then remaining will be adjacent to X in C25 bar. 24 minus 2 is 22. There are 22 vertices which are adjacent to X. Since this structure is symmetric, then every vertex, even vertex Y also will have same degree 22. Now I calculated every vertex degree, I got 22. Understand? 22, 22. So if every vertex degree even, then the graph should have Euler circuit. But condition is even K regular graph has same condition. Every vertex degree even. But C25 bar is connected. But K regular graph may not be connected always. Why C25 bar is connected? I will prove it here. Since C25 bar has a symmetric structure, why symmetric structure? Because whenever a graph has C25 has symmetric structure, because every vertex has same kind of adjacency, then when you apply complement, here the corresponding vertices definitely will have same kind of adjacency, right? So that's why what I prove is I prove that X is connected to everything first. Okay, if X is connected to everything, since X and Y doesn't have any difference, so Y is also connected to everyone. Similarly, Z is also connected to everyone, so on. Okay, so my idea is I prove that a random vertex X is connected to everyone. If I do that, it is like proving that every vertex is connected to everyone. Okay, let's start with C25. In C25, locate vertex X, but we have to prove that X is connected to everyone in C25 bar, correct? So here first focus on C25 because C25 bar is depending on C25 structure. So here X is, let's say, connected to two vertices. They are Y comma Z. Then other vertices, how many? 22. So these 22 vertices are not directly connected to X. Then definitely X is connected to all the 22 vertices. Now our goal is to prove that X is also connected to Y and Z. I just proved that in C25 bar X is connected to all these 22 people other than YZ, because we know that complement property, right? Next, so we have to prove that X is connected to Y, X is connected to Z. So here since X and Y are adjacent, definitely they are not adjacent here, correct? But we have to prove that there is a path. For that I take a vertex which is not adjacent to X, not adjacent to Y. Definitely there will be one such vertex. So let's say that is W. W is a vertex which is not adjacent to Y, not adjacent to X in C25. Locate that W in C25 bar. Okay, since X and Z, W, here it is W, X and W are not connected directly, in complement it happens. So X to W there is edge. Since W and Y are not connected here, in complement definitely they will be connected. So finally there is a path from X to Y through W, X to W, W to Y. Hence I proved that X and Y are also connected. So now X is connected to 22 other people and Y. Now we have to prove that X is connected to Z. Same way, what I do is I can take one vertex, let's say anything, let's say T, which is not connected to X, not connected to Z. That means connected means adjacent. Let's say T is a vertex which is not adjacent to X, not adjacent to Z. Then if you come to complement, then X and T definitely will have direct edge. T and Z, since they are not connected directly or there is no adjacency here, definitely there will be adjacency here. So X is connected to Z, you see, X to T, T to Z, here connected, and of course indirectly, not directly, understand? So X to Z there is a path. Finally I proved that in C25 bar X is connected to every other vertex directly or indirectly. That means there is a path from X to every other vertex. Understand? So similarly, every other vertex has same kind of structure like X, then they also will have connections from that point to every other vertex. So finally that's why this graph C25 bar is connected. Understand? Any connected graph, C25 bar is connected graph and every vertex degree is even, then definitely that graph should have Euler circuit. That's why option C is the right choice.